So as our little starter activity today, I asked you to recite the reaction between methane and chlorine. In the past we used bromine, but you're going to have to be comfortable writing down the overall reaction, and there's no getting away from it, but you're going to have to practice and learn this reaction. There is something missing from that reaction, which some of you put on top, but not many of you, which is that this reaction requires UV light. And it's what we call the free radical substitution mechanism. There's nothing here that's not already in your notes. Okay, so you don't need to write this down if you don't want to. But I would like you, and I'd like you to be able to, you should be able to, if you're going to get the grades that you are wanting to get, you should be very comfortable just producing. This is standard level. It's going to get harder for IB high level. But there's a mechanistic stepwise process that takes us through this reaction sequence bit by bit, and that's what we call the mechanism. The first step of that mechanism was called initiation. Can you write out the initiation step? You need to be covering up your notes so that you can't see it. So let's do that. Put it on the board. So what we wrote out and practiced several times last session is that chlorine-chlorine bond breaking. It's breaking because it's weak, long, because chlorine is big, and under UV light that breaks. We've got to start the arrows in exactly the right place. They've got to be from the middle of that bond, and we end up with 2 chlorine atoms. That's the homolytic cleavage, homolytic fission that we learned about. I'll just remind you, now that I said to you no homework, but I did want you to practice these in your own time. If you're going to get any good at this, you've got to spend 5 minutes here, 5 minutes there practicing. Then it was propagation 1, which involved the chlorine that's just been produced, the chlorine atom, the chlorine radical that's just been produced, reacting with the methane. What are the 2 products of that, please? Away you go. The chlorine radical simply takes a hydrogen off the methane molecule. So the hydrogens are coming around the outside of the methane. Chlorine comes along going, I'm looking for something, and it catches that and snips off one of those hydrogen atoms and makes HCl. And what you're left with is, of course, another radical. Right? You've got an odd number of electrons overall on this side, you're going to have an odd number of electrons over here. And that was the formation of the methyl radical. All right. So I'm kind of showing you that you're not going to be able to do this from guessing. You're going to have to learn it. And yes, I've tried to do it in such a way that you understand it, and when we've got everybody here, I'll go through it in a slightly different way to try to help you understand it better, but I need you to practice it. So P2 involves that methyl radical, because that's not one of the products, so it has to be used up in step 2. And the first step involved the chlorine radical reacting with methane. So step 2 must be the methyl radical reacting with the chlorine. What are the 2 products of that, please? For this one. But yes, you end up with the product. So the first step involves formation of one of the products. The second step involves formation of the other product. So you end up with the products that are actually made in this reaction, right? And then you regenerate the chlorine radical, which allows you to do P1 again, and then it happens over and over and over again. That's what's going on there. And it's balanced, right? We've got 1 carbon, 3 hydrogens, and 2 chlorines on both sides of that reaction. And I want you to now, to each write, there are 3 termination steps. You will choose 2 of those 3, write out 2 termination steps, please. And hold them up, whatever you've got. Hold up your boards, please, people, so I can see what you've got. Yeah, so these 2 radicals coming together to remake a carbon-carbon bond or a Cl-Cl bond, or the third possibility was that one. So the 2 different types of radical in the pot are CH3 dots and Cl dots, and they can come together in any combination to make a product. So they're the termination steps. So most people knew those, but you've got to practice the sequence. We're going to practice it again to make sure you can't see anything. You're going to go back onto mini whiteboards again, and you're going to do a different one. Now I'm going to try to use this as a teaching point as well. So it's a little bit different because it's something there's a couple of things I didn't cover, which is that this reaction can be done with other alkanes, right? So let's go through the process, imagining this time we've got C, because you can't see it, C3H8 reacting with Br2 this time, on an overall reaction. Make sure you can't see the notes, please. So you end up, this is free radical substitution. So one of the hydrogens is swapped for one of the bromines. That's all it is. So you get C3H7 So we lost a hydrogen and replaced it with the bromine plus HBr. Right, so that's a related reaction to what we've been doing. It's exactly the same mechanism as before. Some of you remembered the UV, some of you didn't, and that's okay. But you're going to need to do it overall. So again, that's the overall reaction. Don't get muddled up between the overall reaction and the mechanism. Let's write out the mechanism for that step, one step at a time, please. Again, without looking at your notes, show me the initiation step, please. So it wasn't very neat, this, was it? Let's get that neat. So that's the initiation step, giving 2 bromine radicals. And the bromine radical reacts with C3H8 to give what 2 products, please? You've got to balance it. You've got to have the same number of carbons, hydrogens and bromines on both sides. And if you've got a radical, make sure there's a dot on it. But you're getting there, you're getting closer. Yeah, good, much better than first time round. So you've got the bromine radical reacting with the propane, ripping off a hydrogen from the propane to make the propyl radical this time, and HBr. So the learning point here is that this free radical substitution can happen with any alkane, not just the ones that we've been shown. And then propagation 2, please. I'm going to give you no help with this one. Go. Waiting for some of you, because you've not yet got it into your heads yet, but you're going to need to do that. But in the second step, this time the Br2 is used up, reacts with the propyl radical to give you the product and reforms Br dot. Let me highlight a couple. I'm not going to do the termination step this time. Let me highlight something to you, just to remind you something I've said. So I'll just have, you just don't need to be writing anything now, just listening. So the initiation step kind of stands alone, and it's the thing that just triggers the reaction. Maybe only 10 or 100 or 1,000 bromine molecules get broken down, and there's trillions and trillions and trillions of them still in the pot. So there's an enormous amount of that and that in the pot, and a tiny, tiny little bit of Br dot. But that's what triggers the reaction, starts it off, okay? So what happens, and I'm going to go beyond the scope of the course here now, just to show you what's going on. There's a few more of you here, so I'll do it. But so the Br dot is in there, and the things it can react with are the reactants that are in the pot, right? I'm just going to do ethane, just so that you can see what's going on. The other thing it could react with is the other thing that's in the pot. There's nothing else in the pot. The 3 things in the pot are the ethane in this case, bromine in this case, and a tiny, tiny, tiny bit of Br dot that's been made, right? It has to react with one of those 2 things. So if you're stuck on propagation 1, it has to be the tiny bit of Br dot you've made from the initiation. It's either going to react with the alkane or Br2. Now, let's pretend for a minute we don't know what happens. The Br dot, let's pretend it reacts with Br2. What would happen? What would happen is that this bromine radical, that electron would combine with an electron from here, and the other electron would go there. You end up with this. So that is the same as that. So we call it a non-productive reaction. So that does happen actually. But you can't see it because you've got a bromine molecule and a Br dot will turn into a bromine molecule and a Br dot. And you can prove that with radioactivity studies and stuff, all sorts of clever stuff, but it's not productive, so we didn't write that down. So it has to be the Br dot is reacting with the other reactant, which is the C2H6 in this case. And what it's doing, this is the bit you don't need to know, you might find on videos or books you're looking at, but you don't need to know how to do this. This electron here is becoming one of the electrons in a new bond. And one of the electrons in here, in this covalent bond here, or any of them, is going to combine with that electron to make a bond between bromine and hydrogen. The other electron that was in that bond is going to go and sit on the carbon. That's what's actually going on. If you work that through, you end up with HBr, which you know is one of the products, and you end up with this radical C2H5 dot. That's what's going on, just so you see at a slightly higher level, just so maybe you understand a little bit better what's going on. But taking it back a stage, in propagation 1, we look up here, the Br dot has to react with one of the reactants, So it has to be this one because that would be non-productive. And you're going to generate one of the two products, because one product comes from reaction 1, one comes from reaction 2. So the Br dot reacts with this stuff, and we know that you end up with the HBr forming in that first step. And therefore, the second one is dead easy. It has to be the bromine reacting the second one with the radical we just produced, getting the other product. So you can kind of, it helps you to remember if you can kind of realise that one of the reactants used in one pot and one reaction giving you one of the products, the other reactant is used in the other reaction giving you the other product. It helps you to sort of maybe think about it when you're practicing and learning. All right, there's one more learning point I'm going to make. So let's say we've got, so if you just rub out the stuff you've just done, this time, and they don't really ask this, but it is one of the issues associated with free radical substitution. Let's pretend we've done a free radical substitution already and I've generated some C2H5Br because I've had my ethane and it's been brominated, right? If there's bromine still in the pot, which there might be, there can be a second and third and fourth and fifth and sixth substitution in theory because there's still hydrogens on there, aren't there? So it can substitute multiple times. You can get C2H4Br2 and it can substitute again to give C2H3Br3 and so on and keep going. There could be multiple brominations, you get multiple hydrogens. Could substitute this one, then this one, then this one, this one, this one, this one, this one, this one, and this one. Could do all of them, and that's one of the issues associated with this chemical reaction. It's not very clean. You get multiple products, you get byproducts. Remember learning at GCSE, while you don't get 100% yield, byproducts form. This is an example of byproducts that can form reactions that you didn't want to happen. It's very rare that I've seen. I think it's even in the syllabus from memory, but I don't think it's now there. And I haven't seen recent questions on it where you have to state it as an issue, but it's clear that it would be an issue potentially. It could over substitute, give you wrong product, mixture of products or whatever. Okay, so that's it for now on that. My request to you, firm request to you really is try and spend just, as I said last time to you, 5 minutes here, 5 minutes there, just practicing that, and it will get so much easier because it's not that bad really, because you can all do it again now. Right. Alkenes. Let's spend some time on alkenes now. I'm going to cover all of it, but most of you did GCSE triple, and you therefore will know everything that I'm going to talk about, and you just need to know it. You just need to know it really well. Hello. So, where's my mouse? And this is entirely really a rehash of GCSE. So, what I'm going to cover is some of the reactions of alkenes, and we'll talk about the mechanisms of those next year. So, even though it's a little bit mentioned in standard level, we're going to do all the mechanisms from scratch in the new year. Right. So the first thing is alkenes are more reactive. And that's because of that double bond that they've got. And they do lots and lots of reactions. They do what we call addition reactions mostly. Some of you might remember me doing daft things I'm talking about, like when two reactants become one, two reactants become one product. Right, so they undergo those addition reactions because of the nature of the double bond, but you'll study the nature of the double bond with Mr. Craig at the start of next year when we do stuff on high-level bonding. I talked about it briefly with you, but I'm not going to do any more than that. So we'll study alkenes in a bit more time later on. What we so the first two alkenes rest. In all of these examples, I'm going to use ethene as my example for now. We'll look at other ones next year, but they're all the same. It could be propene, butene, pentene. All the alkenes do the same thing. So they react with halogens. You've seen this bromine. Well, if you just have normal, straightforward, pure bromine, you end up with an addition reaction. And the hydrogens that were on the carbons stay on the carbons. You add to it the bromine molecule. And the thing I want to get across to you, more than anything else, is that the bromine molecule will add across that double bond. In other words, one of the atoms of bromine from the molecule goes to one carbon, and the other one goes to the other. So it's 1-2 addition, if you like. So I'll call it 1,2 dibromoethane, which is what it's called. One, 2 dibromoethane, sorry, is the product there. And you will remember the colour change from orange to colourless as you do that reaction with bromine water. We will learn eventually, I might as well tell you this now, this is what we call electrophilic addition, and electrophiles are reactants that are attracted to negative charges, right? And so the bromine is acting as something called an electrophile, but there's no point covering that in detail until you've been taught about pi bonds properly and sigma bonds properly and why these reactions take place. So I'll say all for higher level. So another example of a reaction you need to know might be the reaction with HBr. This could be HBr or HCl. I'm going to use HBr. So sometimes teachers will call it HX, X representing a halogen. And what you end up with is 1,2 addition again, exactly the same. So you get the 2 carbons with the 4 hydrogens in the same place they were originally, but then the H goes onto one carbon and the Br goes into the other, and this stuff is called bromoethane. Exactly the same reaction with a very similar mechanism, which we'll learn next year. Another one you learnt last year, which you need to know again, is the reaction between an alkene and water. Although water doesn't work, it needs to be. I don't know why that's wonky, that bond there, by the way, as the other ones are. Water, you can't just use plain water. You have to use water gas that we otherwise call steam, right? So steam is used, has to be done at a high temperature and in the presence of a catalyst. And the catalyst you would typically use might be something like phosphoric acid, a strong acid, phosphoric or sulfuric acid. And what you find, again, we'll look at the mechanisms next year, is that the water molecule is, of course, a hydrogen and an OH. And there they are. And you can see, hopefully, that you would end up with this molecule, which you all know is that a primary, secondary, or tertiary alcohol? Show me with fingers if it's primary, secondary, or tertiary. Yeah, good. Yes, it's primary alcohols, otherwise known as ethanol. This is one of the ways of making ethanol, which you learned last year. Nothing new there. Another reaction you learnt last year, most of you, is something called hydrogenation. And if you add a hydrogen across that double bond, you end up with just the alkane, which is ethane, of course. You would need to do that. You were told at GCSE you need to do that in the presence of a catalyst, but that's all you were told. You really need to know now that that's a nickel catalyst. But there are other ones you can use, but you need a nickel catalyst, and we've done it at a fairly high temperature, something like 150 degrees C. Don't worry about knowing that number specifically, but get in your head that that's a way that you would do that reaction. So again, it's an addition reaction. They're all the same. They're always all the same. Nothing different between them. We'll practice them together in a bit. Right, so they're the reactions really. What I haven't covered is, of course, combustion, complete and incomplete combustion. So I'll mention that briefly now. All I'll say is more likely to undergo incomplete combustion and you end up with an evidence for that is you get a smoky flame. That's all I'm going to say about that. But of course they can undergo combustion because they're just hydrocarbons, right? So you're not going to be asked about margarine or hydrogenation of fats, but it's a little bit kind of a bit tocky, isn't it? A little bit kind of along that kind of fluffy edge of the course. So an example of when this reaction is used is when unsaturated fats are turned into saturated fats. You probably know a bit maybe about how, maybe you don't. I'm just going to pause this. So saturated or unsaturated fats are more likely to be liquid, and the properties of a particular margarine or spread or whatever people want to use in the food industry might be different from what they want. So these are all trans fatty acids. You can get cis fatty acids with double bonds that are the other way around. Remember, you can get trans and cis. But you can also get fully saturated ones, and hydrogenation results in that. So it's pretty well known that saturated fatty acids tend to be less healthy than unsaturated fats. So hydrogenation is used to change the properties, but it can also change, or have problems associated with health as well. So again, it's an addition reaction, but addition polymerization. Again, exactly the same as GCSE, so I'm really not going to hang around. Addition polymerization will be taking the alkene, like ethene, N molecules of them, and then these would be the monomers. And what happens is they join together in a long chain, which we call a polymer, and they are in these kind of 2 carbon units. We've always got a 2 carbon unit with square brackets around it. Did you do this at all? This is the first time you've seen this. Okay, fine. I can't remember what was in the trilogy course. So you end up with this sort of thing here, and whatever is in the positions of those hydrogens gets transferred to the other side. So if there's a CH3 here, there'd be a CH3 here, for example. This is the polymer. And however many monomers there are, N monomers, the polymer chain is that many molecules joined together. Right, so what I'm going to do is a couple of examples of this on mini whiteboards. And so if I tell you the monomer is chloroethene, can you please on the mini whiteboards draw polychloroethene? So you're right, this is polychloroethene. You might want to label it up and draw it in a sec. For now on your mini whiteboards, draw propene, and then once you've drawn propene, can you underneath or next to it, wherever you've got room, try and draw polypropene. So propene first and then polypropene next to it or near it or something. So for propene, easiest way to see it is if you draw propene like this, then it's really easy to see what's going on. Once you've done it a few times, it's been pointed out that you've done it wrong a few times, you start getting it right. There's always a 2-carbon unit, carbon A, carbon B. You end up with that, and that's polypropene. But that's the way we do that. That's common to get that wrong, so don't worry. Basically, that's it. That's what you need to do for alkenes for now. We're going to come back to alkenes and study them in a bit more depth. We're going to look at reactions in more detail next year. But this, that's your starting point. Expecting you to know this and try and learn this stuff if you possibly can. So we'll practice it a bit in class, but you're going to need to do a little bit in your own time as well. So I'm going to stop there.